a little bit on the board here before we get started, okay? All right, we have a 300-gram object that's dropped from a resting position on an unstrained spring. We want to find the distance the object falls if the spring has a constant of 20 newtons per meter. Okay, now what you're going to run into here, and I'm not going to lie to you, this is the math itself on everything in this unit is really easy. In comparison to some of the math that we've seen, every single question is very simple. But conceptually, this unit is a pain in the rear because the questions are so all over the place. Also, and I told you yesterday, and tomorrow we're going to use this, I'm going to stay away from, for the most part, the vertical mass spring systems. Okay, because once we have vertical mass spring systems, we have an extra force to think about downward, and we have an extra energy to think about because of gravitational potential. All right, so both force equations and energy equations are harder with it being a vertical problem. So we're going to start off nice and easy with mass spring oscillations horizontally tomorrow. Those are hard enough as it is conceptually. All right, but this one just is a little bit tougher. Okay, we have two concepts that we have to think about on these problems. And it's hard to figure out which one to go with. You have to make sure we're determining whether we're going to be using force concepts or whether we're going to be using energy concepts. Okay? Remember, force concepts is more focused on whether it's balanced or accelerating. Do we have any knowledge of the acceleration of this? No. And on this one, is it balanced forces throughout the motion? No, it's not. So this is a little different than what our lab was. Remember, in our lab, we put the mass on the spring and we lowered it to its relaxed state. Right? We're in the middle of the motion, so when it lowered down, we were right here. We had balance forces up and down. Okay, but now we're dropping the darn thing. So now we need to switch to energy concepts. Okay, so let's look back in our lab. We did force spring minus mg equals 0, so we said that kx equals mg. Okay, that's what we did in our lab last Friday. Okay, what type of energy is stored here? And gravitational potential. We have two different potentials now, so we need to keep that straight. Okay, so we're going to have gravitational potential here. Remember what I keep telling you guys to do with gravitational potentials. Set your lowest point in the problem as 0 meters. That makes it a heck of a lot easier. So if we make this line right here 0 meters, does it have any gravitational potential at the bottom? No. Does it have any kinetic at the bottom? Why not? Okay, where's the kinetic energy going to be the greatest at? I know, that's why I said the conceptual part's the hard thing on these. It's nothing on the math. At the instant I drop it, what's the acceleration? Negative 9.8. Okay? But then it starts accelerating downward, but after a while it starts slowing back down to a stop. So there is no kinetic energy here. So the greatest kinetic energy is actually right in the middle. Okay, is everyone with me there? All right, so that means that there's no gravitational and no kinetic. That means the only energy at the bottom is an elastic. So we're setting our two potentials equal to each other. Got it? How does H and X relate to each other? They're the same because they're both D. Okay? So when we hung the mass on the spring, this is our equation, and if I rearrange that, I'm going to have x equals mg over k. And if I drop it, notice what it's going to be. It just goes twice as far from when it would be in this relaxed state. Does that make sense? It's kind of common sense, folks, anyway. You take a mass, you put it on a spring, you lower it down, you let it reach equilibrium, it's going to be here. If you drop it, it just goes twice as far. Okay? Everyone good with that? Okay, so somebody calculate that. I don't want to calculate it right now. 0.294? Okay, 0.294 meters it is. I hope. Everyone okay with that? All right. So that's going to get you started on the simulation today. Okay, now I will make sure as I come around, because it's really important you get the first measurement right when you do this, because if you don't, the rest of it's just going to suck all the way through, because this simulation is going to be really hard if you have the wrong number on the spring constant. All right, so go ahead and get on your laptops. Let's get this opened up.